Hello and welcome to the second lecture of the module Decision Making for Autonomous Robots. This lecture will be all about planning, how we can get robots to move between different points so that they can perform useful tasks. This lecture will be split into two parts. In the first part, we have an overview of the planning problem and general approaches for solving it. Then in the second part of the lecture, we move on to look at specific solution techniques to solve planning problems commonly being used in robotics. So let's start with some motivation. Why do we need planning at all? Well, here we see examples of different autonomous robots operating in various environments to perform tasks that are useful to us humans. We have aerial vehicles, such as these drones. We have a humanoid robot, a manipulator operating in an orchard, an autonomous vehicle, and an autonomous surface vehicle that works on a lake. Despite their differences, what these robots all have in common is that they need to move, and the success of their mission depends on them reaching a particular point in the environment so that they can perform some kind of action. In this lecture, we look at how we can solve these problems so that the robots can execute their missions successfully and in a safe and reliable manner. Commonly, the path planning problem is also known as a piano movers problem. Why? So let's say we have a CAD model of a piano, as shown here. And the problem is how to transport this piano at different places in a room or even to a different room. Now, this is a difficult problem because the piano is a rigid body that can translate and rotate in 3D space. So you know this problem if you ever had to move furniture. You have to tilt it just the right way so that it can fit in through the door. Path planning is very similar to this problem because we need to move the robot to somewhere where we want it to go. In classical planning problems, we say that the optimal path is also the shortest one. So the shorter a path, the closer it is to the optimal and the better it is. Later on in the lecture, we'll also look at different ways of quantifying optimality. For example, minimizing the energy of a trajectory. But most of the lecture, we focus on actually finding the shortest possible path between two different points in an environment. So in practical robotics applications, the planning problem presents many challenges. First, we need to account for the physical constraints of the robot, including its geometry or shape, its kinematics, and its dynamics. So, say we have a vehicle that can only steer in a particular way. We can't generate a path using our path planning algorithm that can turn in arbitrary ways. We need a path that actually respects these constraints so that the robot can physically execute the motion in the real world. Then, there might also be several sources of uncertainty that we need to take into account. There could be, for example, uncertainty in the sensor data or the measurements that the robot takes in its environment, the observations that it makes. Real-world sensing data is noisy or incomplete, and as a result, we can't exactly trust everything that the robot observes with its sensors. Another source of uncertainty is actuation uncertainty. So if we tell the robot to execute a particular action through its control interface, how sure are we that the robot actually reached that point? In some planning problems, these sources of uncertainty, sensing and actuation, are negligible, but in others they can be quite substantial. So we might need algorithms that actually take them into account when they generate new plans. Finally, as we will see in this lecture and throughout the module as a whole, one key issue that emerges in planning is that of scalability and computational efficiency. So consider a UAV moving in three-dimensional space that can both translate and rotate. The planning problem for this type of robot involves optimizing many parameters because it has 6 degrees of freedom. And if we want algorithms that can run on board and in real time on the robot, we need to make sure that they're efficient or fast enough so that they satisfy the limited computational resources that are available. So in other words, when we design the algorithms, we need to pay attention to how computationally efficient they are with respect to the requirements of our problem. Finally, there might also be dynamic or moving obstacles in the environment, such as pedestrians or other robots, that we need our planning algorithm to take into account. So we might want the robot to sense these obstacles and avoid collisions with them as they appear. Now, before we move on into more details on the planning problem in particular, let's have a recap of what an autonomous system is and what its internal architecture looks like. So this is also called the see, think, act cycle, and it tells us all about how the robot is interacting with its real-world environment. So on the bottom of the figure, we can see the environment, which represents everything outside in the space where the robot lives and operates, apart from the robot or the agent itself. The robot uses different types of sensors, such as cameras and laser scanners, in order to perceive things in its environment. And from this, it can extract information in order to build a map and localize itself within it. So in unknown environments, the robot is doing both localization, estimating its state, and map building at the same time. And this is also known as the simultaneous localization and mapping problem. But in this lecture, we mostly focus on environments where the map is initially known. The robot can then use its estimated position and the global map in order to plan a path with respect to some mission commands. This tells us physically what we want the actual robot to do and what its motion should look like. Then this path can be sent to the robot actuators so that it can physically execute the motion in the real-world environment, and this is called motion control. So during a mission, this cycle, see, think, and act, repeats continually, and this is how the robot is engaging with its environment. So one distinction to make again is that on the left side of the diagram, we have processes which are associated with how the robot interprets and understands the things in its environment using its sensors and an internal model. Well, on the right side, we have processes of planning and control, which are more about acting and what we want the robot to do. Specifically, in this module, we focus here on the block of cognition and path planning on the upper right side. So again, as input to this block, we have a global map of the environment as well as the estimated robot position, and output is the path. And one distinction to make here, just to avoid confusion, is the difference between planning and control. So whereas planning is associated with finding that particular path in the environment on what we want the robot to actually execute, the control block is responsible for interfacing with the real world and converting that path into commands that we can then send to the robot's actuators and motors so that it physically moves. So in other words, control is a more low-level task than planning. Now, if we zoom in more in the planning block, what does this usually look like? So classically, we have what is called a layered planning architecture for robots. It consists of global and local planning. Global planning accepts as input a map of the environment, for example, this occupancy map, and data from the sensor, which corresponds to the robot's estimated state with respect to the map. And then the global plan can provide us with some sub-goal in the environment as to where we want the robot to go on a higher level. And this is typically done on a low frequency, for example, on the order of seconds, so not very often. In contrast, the local planner operates at a much higher frequency, typically on the frame rate of the sensor itself. And what's happening here is that the local planner is responsible for taking new sensor data as it arrives and reacting to it in order to perform corrective actions. For example, if a robot is executing a global plan and it encounters an obstacle, the local planner can detect that and then make the corresponding corrective action. This adds an extra layer of safety. Then the local planner sends the commands to the controller. So if we didn't have the central block of the local planner, what we would be asking the robot to do is simply just to go somewhere in the environment according to the global plan. And this could be very unreliable and very unsafe, especially if there are dynamic things that are moving on in the environment, or if we have a lot of actuation noise, the local planner can effectively correct for that and make sure that the robot is executing the mission successfully. So this is the layered architecture of planning. And in this lecture, we look mostly in the upper block here of global planning, but it's important to understand how this actually works in practice, and that we do have an additional layer here. Okay, so now that we understand the general architecture and the internals of an autonomous system, we can move on to what is actually planning. So the planning problem is associated with finding a sequence of valid configurations leading from a start configuration to a goal configuration. And it's important that this sequence does not lead to any collisions or self-collisions of the robot. So we've all done this before if you had to go to the supermarket and hopefully haven't collided with anything. You have a certain point that you're starting from, a certain goal that you want to go to, and if there's obstacle in between, the robot should simply avoid it. This is relatively easy for us as humans, but as we will see, for robots it's substantially more complicated. So to make this a little bit more specific, the planning problem accepts the initial configuration, the goal configuration, a model of the robot, including its geometry, kinematics, and dynamics, as well as, in this case, a map of the environment, so where the obstacles actually are. And the output should be this path, leading, connecting the initial to the goal configurations. Now, important distinction to make in terms of motion planning is what is a path. When we talk about paths, we simply talk about the geometry of where we want the robot to go to in the environment, for example, to avoid obstacles. So this is something that we can simply draw in a map of the environment. And there is a difference between paths and trajectories, which also include time information. So not only the positions, but also their derivatives, such as velocity and acceleration. So if we know the trajectory of a robot, we know exactly what the derivatives of its position are at each point, and this leads to a slightly different and more complicated problem than path planning alone. So in this lecture, we mostly focus on the problem of path planning, the geometry, but it's important to be aware that trajectory planning methods also exist. Just to give another example, another way of appreciating this is, for example, if you're using Google Maps and you want to navigate to a particular location in your city. And what Google Maps shows you is the route that you need to take, whether you're walking or cycling or driving, in order to get there. So this corresponds to a path. But let's say if you're driving, there are different speeds you can take in order to get there, hopefully without breaking any speed limits. You might accelerate faster or decelerate at certain points. So there are many, many trajectories associated with a particular path according to how fast you're actually moving. And now just to draw the distinction in the scope of this module between planning and decision making. So these terms can be interpreted in different ways, but in this module it's important to draw the distinction in terms of the different tasks the robots have to execute. So for example, here for planning, we were just concerned with reaching a particular goal configuration. But in decision making, we ask the question, where should that goal configuration actually be in order to optimize a particular objective? And then we have, for example, several points where we can select B and then we can apply a planning algorithm to get there. So the main difference is we ask where with decision making and we ask how with planning. A decision-making problem, which we cover in the next lecture, could be relevant, for example, and it's an application that we will keep coming back to, is if the robot is acting as a mobile sensor. So if we have a sensor that we can move to any point in the environment, the question is, where should we put that sensor in order to get the most valuable information? For example, let's say we have a temperature sensor and we want to focus on areas of high temperature. There are several possibilities as to where we can take the next measurement, but based on our map of the model, we might have a preference to one location where we think has the potential to have a very high temperature, and we would then take the measurement there. So just to understand the differences between planning and decision making here. Now we go into a bit how we can formulate the planning problem more mathematically. So planning is typically done in terms of configuration. What is a robot configuration? Well, it's the minimal set of parameters that we need to specify the robot's degrees of freedom. So if we know the robot configuration, then we know exactly what its position and what its pose are. And of course, this is relative to a reference frame or a fixed coordinate system. So we have some kind of origin relative to which we specify the robot configuration. So let's have a look at some examples. So let's say we have this vehicle moving in a 2D plane that can also turn. Its configuration can be given by the two-dimensional position, so x and y here, with respect to an origin. So this is simply the Cartesian plane. And we also have theta, which is the orientation of the robot with respect to a direction. So if we know this vector, then we know exactly where the robot is on this plane and which direction it's facing. On the right, we can see a slightly more complicated example. So here we have a manipulator robot, which has several links attached to it by joints. And so how can we develop the configuration here? Well, what is usually being done is that we look at all these links with respect to each other, and we can measure their angles with respect to each other as well as their lengths. So in this case, the first link is at angle Q1 with respect to the second one, and also length Q2. So we can put them in our configuration vector. And then what we can do is successively chain these different variables in order to form the entire configuration vector, depending on how many joints the robot actually has. So again, if we know a particular configuration here, we know exactly how the position of all these different links with respect to each other. And so now that we know about configurations, the robot motion planning is typically done in the configuration space, also called the C space, which is simply the space of all possible configurations that the robot can take. One common point of confusion here is the difference between the configuration space and the workspace. So the workspace is the set of points in the physical environment that the robot can reach. Let's make this clearer with some examples. So again, here we have our turning vehicle, and we know its configuration that we discussed. So its configuration space can be simply given by the 2D Cartesian plane in the real numbers, as well as the special orthogonal group of 2D rotations, which gives all possible orientations that the robot can take in these 2 dimensions. So here we simply looked at all the possible values that these configuration variables can take and put them in the configuration space. However, the workspace is actually simply the 2D plane, because these are all the points that the robots can reach in its environment. Analogously, let's move on to the 3D world. So here we have a robot that not only can move in the 2D plane, but also has a height z. And we developed the configuration in exactly the same way. So we have the 3D position, x, y, and z, again with respect to reference. And we also have three angles associated with its orientation: alpha, beta, and gamma. And each of these angles are defined with respect to the reference axes. So again here, just like in the 2D case, the configuration space is given by all the possible 3D positions, as well as the special orthogonal group of 3D rotations, which tells us that this robot can actually turn in an arbitrary way. And again, here the workspace is not the configuration space, but simply the 3D volume, which is the physical space here that the robot can occupy. And so now that we understand the configuration space, we can apply this further to planning. So in planning problems, we typically partition the configuration space into the free space and the obstacle space. These are very intuitive concepts. So the obstacle space is simply all the points in the configuration space where the robot lies in intersection and is colliding with some obstacle. And the free space is simply the complement of the configuration space and the obstacle space. One important thing to note here is that obstacles are actually defined in the physical world. And so we need to convert the robot configuration to that particular space in order to see whether they're physically colliding with the obstacles. So that's why we have this A here, in order to make sure that we convert the robot to the workspace in order to do the collision checking. And here we see a very simple example of an environment. So here the white is the free space, and the light blue are some obstacles, and also we have the edges of the workspace, which obviously we also need to take into account when planning. So based on this, we can now officially formulate our planning problem. So if we have a start configuration and a goal configuration in the environment, we need to find a continuous path tau that satisfies the boundary conditions that at the beginning the robot is at the start configuration, and at the end of the path the robot is in the goal configuration. And for all the continuous configurations in between, this must lie in the free space so that the robot is not intersecting with any obstacles. So here's a very simple example in the previous environment, where we have the red showing the geometric path and with the start and the goal configurations here. And obviously, all the configurations in between are in white, and they're therefore in the free space. So this is what we call a planned path for the robot. Now that we understand how to formulate the path planning problem, what are some key considerations that we need to take into account when we design our algorithms? And there are many. So first we have some robot characteristics. So based on the platform that our planning algorithm is targeted for. We need to know its degrees of freedom. For example, whether it is like a UAV and it has 6 degrees of freedom or less. We need to know the physical shape of the robot so we can see what is the clearance that it can have with obstacles. and there might be motion or dynamic constraints that we need to satisfy. For example, going back to the steering example, does the robot have a steering constraint as to where it can turn? Or perhaps it has to satisfy some smoothness constraints there. Now we can use these robots' characteristics to guide the design of our algorithm. And we have several different properties of the algorithm that we need to consider. So the first an important question is the algorithm optimal? So remember, as we said, in the shortest path planning problem, we're always looking for the shortest path, so the minimal possible distance between two configurations. So are we interested in exactly that particular configuration, or do we just need to find a path from the start to the goal, and we're happy with that? This is a question that we need to ask ourselves, because finding the optimal solution might take quite some more time and be more computationally expensive. So this brings us to the next point. We need to consider the computational and memory cost of our algorithms. This is very important, especially if the algorithms need to be run on board the robot. So if they're very slow, the robot won't be able to plan paths on time, and the mission will take way too long. And as we will see, a lot of the popular algorithms currently being used are driven by the limited computational resources that we have on board physical platforms. Another question that we need to ask ourselves is our algorithm complete? So a complete algorithm will tell us if that they have found the solution, or report failure if not. And there are two different sub-aspects that we want to cover here: probabilistic completeness and resolution completeness. So what is probabilistic completeness? This is if we let our algorithm run. The probability that it finds the solution asymptotically reaches 1. So if we let our algorithm run long enough, then it will find us a solution. This is especially relevant, as we will see, for sampling-based algorithms that are based on random sampling of the environment. And so the longer time we let these algorithms run, the more likely they are to find an acceptable solution for us. Another aspect is resolution completeness. So this is very relevant for example, grid-based planners where we have to discretize the environment. So what resolution completeness tells us, if we discretize the environment finely enough, we're able to find the solution. That's a resolution complete planner. So if we have a sufficient resolution, then we are able to find the solution. And it's important to note that not all algorithms are probabilistically complete and resolution complete. This is something that we need to consider. Another property is whether our algorithm is online or offline. So an offline algorithm, we pre-compute the path and we tell the robot in advance where to go to execute the mission. This is acceptable in some situations. For example, if we have an environment that we fully know and we just want to cover using a coverage pattern. So in this case, we can find a lawnmower trajectory that simply covers that environment if our aim is actually coverage, and we don't need to recompute the plan. In contrast, online planning is about allowing the plan to change during the mission. So if in a particular situation the robot needs to react to something, then we do want online planning. But for online planning, then that goes back to computational requirements. Do we have enough resources to actually recompute the plan? And this is called replanning, recomputing the plan in an online way. Also to be aware that some algorithms can be anytime. So that means that the longer we let the algorithm run, the more likely it is to find the optimal solution. This is a very interesting property if we have, again, computational constraints. So in the beginning, we might just be interested with finding a solution, But if we have more time, we might want to improve it and have a shorter path if possible. This is something that we come back to in the later lectures. How can we develop anytime planning algorithms? Another point, and going back to the content from the previous slide, is the difference between paths and trajectories. So again, in this lecture, we focus mostly on geometric path planning, but maybe trajectories are actually important for us, and this is the space that we want to do our planning in. This is very important if we're considering the dynamics of the robot. For example, if we have a UAV that's very small and agile and it has to execute some kind of aggressive maneuvers. In this case, we're interested in optimizing the derivatives of position in order to make sure that we satisfy smoothness constraints so that we can actually physically execute those commands on the robot. So this is one example of a situation where we do want to plan trajectories and not just paths. Finally, another property to consider is the difference between exact and approximate planning. And what we mean by this is that, say we have a goal location, are we satisfied with the robot just reaching the general area of where that location, that configuration is? Or does it have to be exact? Is it very important for the robot to reach that particular configuration? So when we design our algorithms, these are some of the key considerations that we need to take into account. And when we next look at planning methods, we go back to these considerations and see how they can fit in. Okay, so now that we have a fairly good overview of the planning problem and the key considerations for developing planning algorithms, let's have more of a look into some of the common planning methods that are currently being used in robotics. So here we can see an overview of common planning approaches. So in the rest of this lecture, we're going to go through the top 4 in detail in terms of their description, as well as potential advantages and disadvantages for different applications. Later on in the module, we also have dedicated lectures to search-based algorithms and sampling-based algorithms. So we just cover these ones here in this lecture on a higher level to give you an introduction and also to compare and contrast with respect to different methods. Now, just to make you aware, there are also other categories of planning approaches. So one of them is trajectory planning, which, as we said, also accounts for the time information of the path rather than just its geometry. And in some cases, we want to plan in the space of trajectories rather than in the space of paths. This allows us also to set different types of optimization objectives for the planning problem. So rather than finding the shortest possible path, maybe we want to optimize for the minimum time or minimum jerk or minimum snap path depending on the robot dynamics. Optimizing derivatives of acceleration, such as jerk or snap, could be useful in the case of the UAV, for example, when it has to perform very aggressive maneuvers. Making sure that these derivatives are smooth allows for the smoothness of its controls as well. Finally, just to make you aware, there are also bio-inspired methods which leverage ideas from nature within the planning algorithm. And common examples are artificial neural networks, genetic algorithms, ant colony optimization, and many more. But these are just mentioned here and not covered in so much detail. So let's start with our review of planning methods, starting with geometric methods. Geometric methods leverage concepts from computational geometry in order to capture the connectivity of the free space in the environment. Essentially, we want to create a roadmap, which is a graph consisting of vertices, collision-free configurations, and edges, which are collision-free paths joining vertices together along which the robot can travel. And if we have such a roadmap or a graph, we can apply a search-based algorithm in order to find the shortest possible path from a start to a goal configuration. A common example of geometric methods is the visibility graph. This is a planning method which originated relatively early in robotics in the 70s. And the basic idea is to look at all the obstacles in the environment, for example, these 3 polygons. For each of the obstacles, we look at their vertices, and then we simply connect them to the vertices of all other obstacles that are visible. For example, for this vertex of the left polygon, we can connect it to all of these because there is a direct line of sight. And these then form the edges in our graph because the robot can travel between any 2. Also note, a subtle aspect here is that vertices that are adjacent are also connected in the graph. And then we can connect our start and our goal configuration here in the example to the graph and plan a path using a search-based algorithm from the start to the goal. This can give us the shortest path for polygonal obstacles, such as in this 2-dimensional environment. However, one problem, which may already be obvious, is that using this approach, the robot tends to travel very close to the obstacles. And this is by nature in which we construct the graph. So if there's actuation noise in the robot controls, for example, it might lead to collisions because the robot has very limited clearance when it's traveling close to the obstacles. So one way of resolving this is using a different geometric method, the generalized Voronoi diagram. And here the basic idea is to form these edges by looking at obstacles in the environment and connecting points which are at equal distances between 2 of the obstacles. So essentially, we want to find the edges as the paths of maximum clearance between obstacles, so right in the center. This is called a Voronoi diagram, and it's used not only in robotics, but also in many other applications. Here, note that we also consider the workspace edges as being obstacles, since the robot cannot go outside this area. So here is an example in a very simple, again, 2-dimensional environment of what this might look like. So here the lines are the Voronoi edges, which are the maximum distance between different obstacles in black. And as before, given a start and a goal configuration, we can apply a search-based algorithm to find a safe path from the start to the goal location along these edges of our roadmap. So one benefit of this, as we saw in the figure, is that these paths are rather conservative because the robot has maximum clearance. So compared to the visibility graph, there is less danger of crashing into an obstacle if the actuation is imperfect, because there is a lot of room for error. This is very similar to the way we behave as humans. For example, if I'm walking down a corridor, I tend to stay approximately in the center and hopefully not navigate right along the wall. However, one limitation of this approach is that it could be difficult to compute in high-dimensional spaces. And this is because we need to model all the obstacles explicitly. Also, the paths that are generated might be too conservative. So, especially when we have a corridor followed by a large free space, this might lead to extremely long and suboptimal paths, which we may not want in particular applications. Another issue is that Voronoi diagrams tend to be unstable. So if there are even small changes in the way the obstacles look, this could lead to relatively large shifts in the diagram. So this is an aspect that we need to pay attention to. Finally, there could also be issues with short-range sensors in large spaces. Since if the robot is navigating along a Voronoi edge, and it has a very short-range sensor, it might not be able to see the obstacles. And this could lead to issues with localization and mapping, since the robot relies on these features to localize itself and to understand its environment. Therefore, if we use this method, we need to make sure that our sensor is appropriate. Moving on to a very different method, we can also plan using potential fields. And here we consider the robot to be a point mass that is under the influence of potential, which pushes it in different directions towards the goal. In general, the potential field is made up of two different types. We have an attractive potential, which is associated with where the goal configuration is. This potential serves to drive the robot and pull it closer towards the goal. So this we can see here on the first figure. The black dot here is the goal, and the area around it is corresponding to the part with low potential, so it's easier for the robot to get to there. In contrast, we can also have repulsive potential, which is associated with driving the robot away from the obstacles. So if we had two obstacles in this environment, we would want to intuitively set them in high potential so the robot is discouraged to go there and it is difficult to reach. Potential field methods are based on superimposing or adding these two types of potential. This we can see in the third figure. So essentially, the total potential field is a differentiable function, which is a combination of attractive and repulsive potential. So visually, if we put a robot point here and imagine it as a marble rolling down, it will tend to roll down towards the goal and away from the obstacles. Another way of seeing this is if you have any experience with working with electric fields, for example. So if the robot is a point charge, then the obstacles we can consider as being the same charge, repelling it further away, whereas the goal is the opposite charge, driving it closer together. This can generate a vector field where the vector is pointing towards the direction of the goal. There are several considerations that we need to take into account when we design our potential field. So first is, how do we actually model the potential itself? Well, as we said, we want the potential to be low at the goal, so we can set a distance-based potential as to how close the robot is to the goal at a particular point. But there are different ways of doing this. For example, we can use a linear or a quadratic distance function to achieve this. And this will essentially shape the potential landscape that we use for robot navigation. It's a similar case for obstacles, where we can set the distance to be the inverse of the distance or the inverse of the square distance. And these are considerations depending on how we want our robot to behave. Finally, we have to specify a solution method for solving the potential field. So this is relatively a simple solution, to simply follow the negative gradient using a gradient descent algorithm. So for any point, we look at the gradient of the potential and drive the robot in that direction. This is if we want the robot to go to low potential areas with the negative sign. So here we can see an example where the robot is starting here from the black dot and moving towards the pink. And the darker colors indicate regions of higher potential, which are repelling the robot away, whereas the lighter area around the goal is the low potential area that the robot is attracted to. As we can see, there are 4 obstacles, approximately circular shaped in this environment, and the robot successfully avoids them by taking a path around and driving closer to the goal. So intuitively, this is a relatively simple implementation, also easy to understand. And it also gives us the advantage of using online collision avoidance, because at any point in time, we can nudge the robot in the direction of the low potential field based on the gradient. However, as before, one important limitation is scalability, because to develop the potential field, we actually need to explicitly model all the obstacles in the environment, and this can be quite tricky to do in higher dimensional configuration spaces. And another problem that's inherent to the potential field is that of local minima. And these are configurations where the robot essentially gets trapped. So this can happen, for example, if we have a goal point here and the robot is traveling to it being attracted. But at some point, there is a U-shaped obstacle in front that repels the robot and prevents it from going further. So in this case, as humans, we know that the right thing to do would be to backtrack, go around, and circumvent the obstacle so that we can reach the goal. But using the potential field model alone, this is impossible to do, because the robot will simply get stuck there. It will gain nothing by going backwards, and so it is not encouraged to do so. And this can also happen if we have a goal behind two obstacles. And in this case, at this point, dot where the robot is, the potential that's attracting it to the goal is the same as that pushing it further away. So the robot will get stuck in this local minima. In practice, there are several ways of dealing with this problem. For example, we can encourage the robot to take short walks to escape the local minima problem, or we can develop some more sophisticated potential fields, such as called navigation functions, that effectively avoid the problems of local minima. But these are special considerations that we need to address with respect to our problem, and they're not present with the simple potential field approach that was presented, that is just based on distance. Now moving on to search-based methods, which we have already touched upon. Search-based methods are applicable in a variety of situations in discrete spaces. So instead of having a continuous configuration space, we can discretize it and apply a search-based method in order to find the solution. In general, this is done on a planning graph or a roadmap, as we have seen before, where the vertices correspond to collision-free configurations for the robot in the free space, and the edges are connections of vertices that are collision-free, where the robot can travel. And if we have such a graph, we can apply a search-based algorithm to find a path. And details of how this is done will be explained in the next slides and also in the lecture specifically about search-based methods. But this is to just understand the intuition of where is a search-based algorithm applicable. So this is when we have some kind of discretized representation of our space. And common algorithms that are used for search-based planning are listed here. So we can do uninformed searches such as depth first or breadth search, which you may have heard of before. These basically explore the graph based on a simple rule. For example, in depth first searching, we always look at the node or vertex on the graph that is furthest away from the start and explore it further. In contrast, in breadth first searching, we do quite the opposite. We look at all nodes or all vertices on the same level first and then see if they lead to a promising solution. We also have other algorithms, which we'll see in the next slides, called Dijkstra and A-star. But the concepts are the same. We are figuring out how to search this graph to find the shortest possible path. Here is an example of an application of search-based methods. So we already talked about visibility graphs. And here we can see a visibility graph that was generated by connecting the intervisible vertices of the obstacles. These are shown in the black lines. And then what we can do is, if we have this graph, is specify our start configuration on the top left and our goal configuration on the bottom right and plan a path through them. In this example, this is done using Dijkstra's algorithm, which simply looks at the node or the vertex that is closest to the start and expands it further. So on the green, we can see which vertex is being looked at next to see whether it leads to a good solution. In orange, we can see vertices that are at the fringe of our search space on this graph. Eventually, as we saw on the yellow line at the end of the animation, the robot can successfully find a path from the start to the goal using this method. So this is an example of searching a roadmap. Another way of generating the discretization for search-based methods is using a grid, which is a special case of a graph. So here what we do is we overlay a grid on top of our configuration space in order to capture its connectivity in a uniform way. So here is an example. We have, again, some polygonal obstacles. We have a start and goal configuration. And what we did is we simply overlaid the grid at a fixed resolution and found a discretized version of this state space. So here each cell is actually associated with a configuration. And to handle these different shapes of the obstacles and the polygons, we can use some tricks. For example, applying a Gaussian blur in order to inflate their size and making sure that each cell corresponds to either obstacle or obstacle-free configuration. This way, we can do collision checks in the space of the grid. So again, the reason why we want to do this is because discrete methods actually enable these search-based algorithms. Otherwise, we would have to plan in the continuous space without a concise representation. So there are several considerations, again, if we go for a grid-based approach that we need to take into account. The first is the resolution of the grid. So we can set either a very dense grid at a high resolution or a very sparse one on a low resolution. So on a high resolution grid, we have many different configurations the robot can take, whereas on the low resolution grid, we have a finite number of cells or configurations, a much lower one. So this influences our algorithm in several ways. So first, a high resolution grid enables us to do very fine-grained planning. However, it takes much longer to compute because we have many more configurations there. And so we need to take more configurations into account when we actually do the search. Whereas a coarse resolution grid is much more efficient, it might run into issues, for example, if we have obstacles and the cells are too large, then we do not correctly capture the structure of our free space. So the discretization is also highly dependent on the structure of the environment. In some cases, what we might want to do is a hierarchical approach, where we first plan using a low-resolution grid, and then refine the path further using a high-resolution grid. And some algorithms, as we will see in the later lectures, actually do this. Another important consideration is the connectivity. So this is how we want the robot to move in our grid. So a simple thing to do is just consider four-neighbor connectivity. So if the robot is in a particular cell, it can either move to the top, bottom, left, or right cells. So it has four options for its actions. Another connectivity structure is the 8 neighbors connectivity, which also allows the robots to move diagonally. In general, the way that this type of discretization is done is that we constrain the robot to orientate only at particular multiples of a base angle. So here it's 90 degrees, here it would be 45. So this influences highly the type of paths that we're going to get. And there are more sophisticated algorithms which go around this base angle idea, called any angle algorithms, that allow the robots to move in any type of direction, which may lead to more natural paths, but we have to make special implementation decisions there. So just to give a very high-level overview of how this actually works if we have a grid. So here is an example of a search-based algorithm, Dijkstra's algorithm in practice. And in general, what we're doing here is always expanding the nodes on the graph or the vertices with the minimal distance to the start. So the start is here and we want to go here. And we essentially grow our search space by always looking at the minimal distance to the start. The cyan crosses indicate these nodes that have been explored. And as we can see, there's a sort of frontier that grows and eventually reaches the goal in order to find the correct solution to the path planning problem from the start to the goal. Another example of an algorithm is the A-star algorithm. So the A-star is an extension of Dijkstra's algorithm that not only considers the distance from the start to the goal when expanding the search space, but also it estimates the distance to the goal using a heuristic. This way we can do more efficient searching because we also think about what is the potential distance that we need to travel in order to reach the goal, and not only considering to the start. So it's an informed search strategy that makes use of a heuristic to guide the search. So we can, in these animations, appreciate the differences of using different search-based algorithms in the same type of environment and how they eventually converge to the paths. And we cover both of these algorithms as well as some of the extensions of A-star in the future lecture on search-based methods. So now is a good time to take stock of what we have covered in the previous slides. So in general, the approach to solving the planning problem has been we need to somehow define the configuration space. So is the robot moving in 2D or 3D, and what is the minimal number of parameters that we need to fully specify its configuration in the environment? Then this gives us with a continuous and dense representation of the configuration space. So then what we want to do is discretize the configuration space in some way. And look at different ways of this can be done. For example, we can create a roadmap using one of the geometric methods, or we can overlay a grid on the environment and apply grid-based planning. But in general, the purpose of this step is to convert the continuous into a discrete, concise representation so that we can do planning. Given the discrete configuration, what we then looked at is searching the configuration space, now discrete, using a method such as Dijkstra or A-star. And this is the general approach for tackling these problems. However, at this point, you might observe that all the discretizations of the configuration space we looked at it as a whole. So in other words, we need to explicitly model the entire environment and also the obstacles within it. And as pointed out already, this is quite difficult to do if the obstacles are complex and also in higher dimensional configuration spaces. And going back to our design considerations for planning algorithms, computational efficiency is really a key aspect when we design our algorithms because we need them to be fast enough to run on the robot without taking forever. So what can we do? And this is where the final class of methods that we discuss in this lecture come in, which are sampling-based methods. And these methods are basically motivated by the idea that discretization is an expensive operation, especially in high-dimensional spaces. It is not only slow to find paths, but it also takes up a lot of memory. Consider, for example, how much a grid that is in 2D, how much memory it occupies compared to one that is in 3D and has many cubes associated with the entire volume where the robot is operating. So sampling-based methods go around this by sampling. So the insight is that, well, collision checks and visibility checks are a fairly simple operation. We just connect 2 points and we check whether this constraint is satisfied, whether an obstacle is in between. So what we do in sampling-based methods is we sample the configuration space randomly, and then we do collision checks in order to create a roadmap. So this avoids us from fully modeling the entire environment and is more efficient because we just need that collision checking operation there. In doing so, we can then construct a graph that consists of the sampled configurations and then plan a path to it. Now, this approach trades off completeness because we don't consider the entire configuration space we're planning, but is much more efficient. So this is a trade-off that we're making here. In other words, we probe the configuration space and learn about it incrementally rather than treating it as a whole in order to gain that efficiency. And common algorithms for doing this, which we'll look at in the next slides, are the probabilistic roadmap and the rapidly exploring random tree and its variations, among others. So let's have a look and further reinforce with ideas using the example of the probabilistic roadmap, which is a common planning algorithm. So the probabilistic roadmap consists of two main stages. The first is the so-called learning phase. So here we just sample configurations in our configuration space and check if they're collision-free. If a particular configuration is collision-free, we add it to our roadmap, and this way we get, again, a map of where the robot can actually go without running into collisions. But rather than doing this from the perspective of the entire environment, we just sample and we check for collisions incrementally. Then, if we have this roadmap, we move on to the so-called query phase, where we actually generate the path. So having a roadmap, we can connect our start and our goal configurations, and then we can plan a path through it using a search-based strategy, because we again have a discretized representation of the environment. However, we generated it in an incremental fashion during the learning phase. So here in blue, we can see a path that was planned between the start and the goal, given the output of the learning phase. And this approach is especially useful for multi-query problems. What are multi-query problems? It is when we may have several planning problems associated with one type of environment. For example, say at first we want to get from here to here, but then in a later mission, assuming the environment remains static, we want the robot to go to a third location. And in this case, provided that the environment stays the same, we can simply use the same roadmap because we already sampled it. The way that sampling is usually done in the learning phase is uniformly. So we just randomly sample and check for collisions. But if our environment has some more sophisticated structures, for example, hallways or corridors that may be tricky to find collision-free paths through, we might need to implement some specialized sampling strategies in those locations. And more advanced methods of probabilistic roadmaps actually look at doing this. Now, so much for multi-query planning. State-of-the-art sampling-based method for single query planning is called the rapidly exploring random tree and its variants. So here, rather than dealing with a roadmap and the environment and configuration space as a whole, we start from a center called the start node, and then we grow a tree, which is a graph with no cycles from that start, which is essentially the root. And here again, we sample configurations in the environment and check if they're collision-free by connecting it to the tree. And this way, we can expand quite rapidly. So in this simple example of an obstacle-free environment, we can see how quickly the rapidly exploring random tree generates a roadmap without actually looking at the environment as a whole. It's just sampling and checking locally for collision checks and adding them to the tree. Here's another animation showing the rapidly exploring random tree in a case with obstacles. So here we have actually quite a challenging problem where the goal is behind the obstacles, and the rapidly exploring random tree is growing, sampling and creating these connections before it stops when it eventually finds a path to the goal. Now, it's important to note, and we'll cover this in more detail in the sampling-based lecture, is that the rapidly exploring random tree and its raw implementation is not an optimal algorithm. We have another approach called the RRT star, which is provably optimal, and this we cover in that particular lecture. So briefly, just the way that this is being done is by using an intelligent sampling strategy and rewiring the tree in order to achieve that optimality. So this is just to give you an understanding of sampling-based methods and how they are different to the other methods we have covered. So with that, we can return to the overview of our methods and compare them a little bit. So here's all the methods that we have covered, as well as some of their properties and comments about them. So one important note here again is that scalability is an issue with these algorithms that discretize the entire entire configuration space and then apply a search-based algorithm. The sampling-based methods are much more scalable, and the two algorithms that we looked at here are the probabilistic roadmap and the rapidly exploring random tree, which offer us these benefits. So, for example, if we do planning with a UAV, we might want to opt for example, an RRT type algorithm for single query problems, because this is more efficient in such a situation. One disadvantage of them that's listed here is that they often tend to produce, as we saw in the animation, rather jagged paths, and this is just by nature in which the tree is being built up in the configuration space. And usually the way that we deal with this is, for example, by smoothing the path in order to make a smooth trajectory of this, refining it in the stage of where we actually incorporate the time information and send the control commands to the robot. So this is an overview of the methods and the different ways that we can address planning problems in robotics. This brings us to the end of this second lecture in the course, which is an introduction to planning. So we started with an overview of autonomous systems and potential applications where we want to apply planning algorithms in order to get them to perform useful tasks and missions. Then we moved on to defining particularly the planning problem. So the aim is to find a sequence of collision-free configurations in an environment connecting a start configuration to a goal configuration. We looked at how this can be done in the configuration space, as well as some of the key considerations that we need to take into account when we design planning algorithms with respect to particular requirements. So this was just from a general point of view. Finally, in the second part of the lecture, we looked at different planning strategies, including geometric, potential field, search-based, and sampling-based methods. We compared them and contrasted them, and in the future lectures, we will have a look at, in particular, search-based and sampling-based methods. Now, the field of planning is rather broad, and there are plenty of additional resources that you can have a look at in order to deepen your understanding of this topic. Some potential ideas for further reading are listed here, and in each of them you can pick one of the algorithms that we have covered or that you have more interest in, and you can look at them in more detail also before the next lectures. So don't be afraid to read around the topic and also have a look at many different examples and many different ways that we can go around to some of the disadvantages that we covered in this course here. Thank you for your attention.